Hi everyone. So in the first video I review the concepts we talked about in the previous chapter about ions and their radii. And the reason I want to talk about those is because in this video we're going to get into exactly how we determine the strength of an ionic bond, and one of the methods that we're going to use rely on the idea of the size of the ionic bond radii, and you can use the sizes that we talked about in the previous video to get at that radii. Okay, so first off, just kind of discuss this idea of a strength of an ionic bond. Okay, how we can quantify it. Well, an ionic solid, something like sodium chloride, solid, for example, the table salt you have at home that you can pour out, it's obviously a solid. That solid, if we look at it in microscopically, you'll find that what it is what we call a three-dimensional crystal. Okay, so a crystal is a special type of arrangement of atoms. It's basically arrangement of atoms, or ions in this case, because this is a crystal of an ionic compound. It consists of the specific structural pattern. This pattern, the structural pattern, is called a lattice. And because this is an ionic compound, the lattice is composed of a bunch of cations and anions. Okay, now I'm going to jump to the next slide and then come back to this slide a little bit after I discuss this idea of a lattice. So what do I mean by a lattice? Okay, so this is your sodium chloride crystals. You can make these crystals very easily. You can, if you look at the solid that you have at home, your salt crystals, your salt solid basically. If you just take those salt and you put it in warm water, you dissolve it, and then you can just let that warm water in a cup sit for several days at room temperature. Eventually all the water will evaporate, and at the bottom of it you'll get crystals that look like this. This is your sodium chloride crystal, NaCl, right? Now if we take this and we shoot this crystal with X-rays, you'll find that underneath that crystal, the structure that makes up this crystal looks like this. Okay, and so the blue spheres here are your chloride ions, the green spheres are your sodium ions. Okay, so you can see what they're arranged in this pattern where it just repeats itself in 3 dimensions. So chloride, sodium, chloride. Obviously if we go here we'll have another sodium. You go back and front, you get that same pattern being repeated. Okay, this particular pattern, this special pattern for sodium chloride, is what we call a lattice. The word lattice comes about from other arts and crafts type of fields, where in cloth design, for example, you use a specific pattern to design a cloth. So for example, in this case, you can see that this particular pattern is just being repeated again and again. So that's the idea of a lattice. So that's why this whole thing here, this crystal, is called a lattice for that reason, because it's repeating the same pattern again and again for this particular group of ions, sodium and chloride. Okay, because we call this a lattice pattern, the strength of an ionic bond is really the strength of the interaction between one of this, let's say this sodium ion in the middle, this green one right here in the middle, that's surrounded by all of these chloride ions, right? So you got one chloride ion here, one chloride ion there, one chloride ion to the top, one chloride ion to the bottom. So that strength of interaction is what we're trying to quantify. Of course we want to quantify one of them, but then it's usually not possible to do that. So we usually express this quantity in per mole quantity. Okay, so if you go back here, that strength of interaction is what we refer to as the lattice energy. Now specifically, the lattice energy is actually the energy that's needed to break that interaction. Okay, so as opposed to measuring the strength of the interaction between the cation and the anion, the lattice energy is actually the energy that you need to break that interaction. Okay, so matter of fact, if so the idea here is the lattice energy is the energy that it takes to bring sodium chloride from a solid state, okay, which is the salt that you see at home, and to basically take it apart into ions, sodium plus and chloride minus, in the gas state. The energy needed for this process, this reaction right here, is what we refer to as the lattice energy for sodium chloride. Okay, so it's the energy needed to break 1 mole of an ionic solid into ions in the gas form. Because of this definition, obviously the sodium chloride is more stable, right? We talked about earlier in the video where I introduced the whole idea of compounds, that compounds are more stable than their separate atoms or ions. So the lattice energy, because it's the energy needed to break that interaction, it must be positive. As a result, it's endothermic. Okay, something to keep in mind here. The energy of the opposite process is what we refer to as the crystallization energy. So that's the opposite of this process. In other words, it's just Na plus in the gas plus Cl minus in the gas going to NaCl. That energy is referred to as the crystallization energy. It's just the negative of the lattice energy. Okay, remember, if we reverse a reaction, the enthalpy becomes the negative, right? So that's what we talked about in chapter 6. Okay, so now I talk about all of these lattice idea, the concept, because it's important now in discussing how we actually measure it, because we want to be able, of course, to know how strong this bond is between a sodium and a chloride, or a magnesium and an oxide, or a magnesium and fluoride, and calcium and chloride, and so on, because the strength of that bond gives the salt, gives that ionic compound certain properties, right? So there are two methods we can use to calculate the lattice energy. One is something called Coulomb's law. If you've done physics before, you would have encountered this equation, which I'll show you in the next slide. And this is just an equation, a law, that's been discovered a long time ago on point charges. Okay, so you can use this equation to basically estimate, in our case, what is the strength of a particular ionic compound, versus another ionic compound. We're going to talk about a much more extended series of steps that are that uses the concept of Hess's law, which we learn in the thermochemistry chapter. Or another way of this to define Hess's law is, of course, a thermodynamic cycle. This particular method is known as the Born-Haber cycle, and I'm going to have a separate video detailing how that works. But in this particular video, I really just want to get through using Coulomb's law to estimate the strength of lattice energies. Okay, so what's Coulomb's law? Well, Coulomb's law is basically it's an equation that Coulomb discovered a while ago. Matter of fact, back in the late 1700s was published. And basically, the law itself is on the forces that act on point charges. But we're going to use the energy form of this, where he said that the potential energy of two point charges, in this case, is going to be equal to the following expression. K times Q1, Q2, Q1 times Q2 over R. We're going to focus on this component of it because this is the part that's important to us. The K is important, but it's not something we can kind of use too much with at this point. This is basically a proportionality constant, and it depends on the environment of the ion. So pretty much it depends on, the specific type of ionic compound you're talking about. But what we're interested in comparing here is we're not going to actually calculate the potential energy for a particular ionic compound. What we're going to do, as you'll see in the next example, is we're going to really just compare, relatively speaking, if we have two ionic compounds, which one has a stronger lattice energy. Okay, so the Q1, Q2 over R is an important concept to understand here, because Q1 is basically the charge of the cation, you can think of it, and then Q2 is the charge of the anion. So we're talking about sodium chloride, this would be +1, this would be -1. We're talking about magnesium chloride, this would be +2, that'll be -1. Okay, it's the charge of each of the ion that you have there. And then R is the distance between those ions, which in other words is the ionic bond length. Okay, so the lattice energy in this case, the way we define lattice energy, remember, is the energy needed to break the bond, right? The ionic bond. So in other words, it's just the negative of this value. Okay, so whatever this value is that you calculate from Coulomb's equation, the lattice energy is just the negative of that quantity. So let's say this quantity you get negative, I don't know, 1,000 kilojoules, for example, the lattice energy would be positive 1,000 kilojoules. Okay. Now let me show you what we're going to use this for. The importance here is in solving problems like this. For example, you have two different ionic compounds here in A, NaCl or MgS. The other one is CaCl2 or MgF2. And the question is which one has the higher lattice energy. And in this case, and the second question is why. Okay. I'm going to go to the next video because I've reached my time limit here. So I'm going to go to the next video to kind of work through this problem, show you how we can process this.